Hello students, welcome to the 54th lecture on particle physics. And in the last lecture we were discussing about SU2 representation of quarks, and then we talked about three objects in SU2 representation. Those objects were U and D quarks. Just to recall what we did on the last turn, we had two objects. Those were U and D. They have been assigned isotopic spin, and the third component of isotopic spin as half plus half, while for D it is half minus half. Then what I had told you, that if you have two half objects, then the combination that you can make is you can go from half minus half to half plus half, and that is 0 and 1. That will be the total isotopic spin. While this we may write it as I1 and IZ1 for the object 1, and this is the third component or the Z component, and this is I2 and IZ2. Don't get confused with it with square. This is 2. There are two objects. This is one object and this is another object, and therefore I is the total isotopic spin of the system where these two objects have been put together. And then I3 or IZ, or you may call it IZ, this for 0 the projection will be 0, for 1 the projection will be plus 1, 0 and minus 1. And therefore what I had told you, that for the two objects the different states that you can form is 1 plus 1, 1 0, 1 minus 1 and 0 0. Then the question is how one would get 1 plus 1 with these two objects, and the answer to that was, since the projections are algebraically added, therefore this has to be plus half to give us plus 1, and 1 we know that 1 can have projection plus 1, and therefore these are the two isotopic spin half objects, and this we are forming from half plus half object. We may call it J1M1, and half plus half object, this we may call it as J2M2. And then I told you that this is nothing but the Clebsch-Gordon coefficient, and this value of Clebsch-Gordon coefficient you can look at the table. This is half plus half, J1 M1, J2 is half, M2 is plus half, and then J is 1 and M is, therefore this is J2M2, this is Jm. Now if you look at the Clebsch-Gordon table, you will find this value to be 1. And therefore for 1 plus 1, what is this? This value is 1. Half plus half is a spin U quark or a U quark object, and this half plus half is also U quark object. Therefore this is U quark in state 1 and U quark in state 2. When we talk about 1 minus 1, then 1 minus 1 we could obtain. There is only one way. When this will be minus half and minus half, this will give us minus 1, and this minus 1 means this is minus half, this is minus half. Therefore what we have this as half minus half, J1M1, half minus half, J2M2, and 1 minus 1 Jm, and this value also turns out to be 1 in the Clebsch-Gordon table, and half minus half is a D object, and another D object is half minus half. Therefore we wrote it as D1 D2. Similarly for 1 0 and 0 0, we found that now what we have two possibilities, and those two possibilities were that in the first state the projection is plus half, and in the second stage the projection is minus half, and therefore this was plus half, this was minus half to give us 0 plus algebraically when we have added them. This is plus half, and then another time this is half minus half, half plus half, and this is 1 0. This is half minus half and then half plus half. This Clebsch-Gordon is 1 by root 2. This Clebsch-Gordon is also 1 by root 2. Therefore, we have taken 1 by root 2 common. Then it was u1 d2 plus d1 u2. Then we spoke about 0 0, and then 0 0, because half minus half will give me 0. This 0 0, just there will be one change here. This will be 0. This will be 0. But the Clebsch-Gordon for this guy is 1 by root 2, but for this guy is minus 1 by root 2. Therefore, for 0 0, therefore the top one is representing 1 0 state and the bottom one is representing 0 0 state. Therefore, this is with a negative sign, and what I had told you that these three will be completely symmetric while this is anti-symmetric. Now we have this situation for the two objects, and this I told you that what we are actually getting is 1 plus 1. This is u in a state 1, u in a state 2. This is similar to two fermions. Both of them are spin half objects. Then spin up state we wrote it as half plus half when we talked about spin, and spin down state as half minus half, which represented a down state. Therefore, for 1 plus 1 is system with spin 1 whose projection is plus 1 is a particle 1 in the spin up state and particle 2 in the spin up state. This is also we talked about in terms of proton and neutron, because proton is represented by isotopic spin half whose projection is plus half, and this is half whose projection is minus half. Therefore, for 1 plus 1 you have the possibility that in both these states you have two protons. Therefore, this is the general scenario. Therefore, this is 1 plus 1, 1 0. This we wrote it as 1 by root 2 u1 d2 plus d1 u2, and then 1 minus 1. This was d1 d2 and 0 0. This is 1 by root 2 u1 d2 minus d1 u2. Everything is fine up to now. Now what we have to do, since we have to talk about the baryons, and particularly first we are interested in non-strange baryons, that means say proton, neutron, delta plus plus, delta 0, delta minus, etc. Therefore, if we want to write the flavor wave function for them, then here we have three states because every baryon is made up of three quarks. Then we discuss the system of two objects, a system of three objects in SU2 representation. And then what I had told you that we have from two objects, these are the possibilities, and then we have to add either an isotopic half plus half is isotopic spin state particle, or half minus half isotopic spin state particle. That means either a u quark or a d quark in a state 3. Now again there is a catch, and the catch is when we consider these two guys, then plus 1 and plus half, when we will algebraically add them up, we will get only plus 3 by 2. And while 1 and half, J1 and J2, let us call to make life simple. J1 is 1, J2 is half, this will go from J1 minus J2 to J1 plus J2, and this is nothing but half and 3 by 2. Therefore, we have J is equal to half or 3 by 2, but 3 by 2 can have 4 possible projections: 3 by 2 plus 3 by 2, 3 by 2 plus half, 3 by 2 minus half, 3 by 2 minus 3 by 2. These are the 4 possibilities, while this guy has the possibility half plus half or half minus half. Therefore, what you see that when I will add plus 1 and plus half, we will get only plus 3 by 2, and that means J should be only 3 by 2. This is not possible because projection cannot be plus 3 by 2. Therefore, when we added 1 plus 1 with half plus half, we obtained it as 1 plus 1, half plus half, then plus 1 plus half will give me plus 3 by 2, and this is possible only when we have a 3 by 2. Therefore, we have got a 3 by 2 plus 3 by 2 state, and this is nothing but U in state 1, U in state 2, now U in state 3, and this is the Clebsch-Gordon, whose value is 1, and this 3 by 2, a particle which has isotopic spin 3 by 2 and whose projection is plus 3 by 2. We have only one particle like that, delta plus plus. Therefore, this is the flavor wave function for delta plus plus. This is the flavor wave function for delta plus plus, and this is completely symmetric flavor wave function. As you can see, the flavor wave function, you can interchange these 3 quarks. We saw that nothing is going to change. Now, similarly, we also spoke about combining 1 minus 1 with half minus half, these two guys. Then in that case, this is minus 1 minus half, and minus 1 minus half will give me minus 3 by 2, and this will give me minus 3 by 2, and that is only possible from J equal to 3 by 2. Now, then in that case, 1 minus 1 is a D1, D2, D in state 1, D in state 2, and half minus half, D in state 3. And then this Clebsch-Gordon is 1. This is 3 by 2 minus 3 by 2. This represents a delta minus state. Therefore, as you can notice, a delta minus state is also made up of 3 D quarks. Now, there is another catch here, and this you should try to understand. If we go back to the previous slides, what I had told you, that if you have a spin like this situation, then 1 plus 1 will be particle in state 1 has a spin up, particle in state 2 has a spin up, while this will be 1 0 will be a spin state, where in the first state whatever particle that is will be in a spin up state. We don't know what particle that is. That can be a U quark, D quark, S quark, whatever it is. But if that represents a spin 1 and whose projection is 0, this will be particle in state 1, no matter what that particle is in a spin up state, particle in state 2 is the spin down state, plus particle in a state 1 is in a spin down state, and particle in state 2 is in a spin up state. Similarly, for 1 minus 1 for spins, this will be both the particles in the spin down states. For 0 0, this would be Particle in state 1 will be in spin up state. In state 2 it will be in spin down state, minus spin down and then spin up. As you can see here also we have 4 possibilities. First 3 they are completely symmetric and the third one is anti-symmetric. Therefore, we have 2 spin half objects. We are combining these 2 spins and we are saying that there are 4 possibilities, 3 symmetric and 1 anti-symmetric, like flavors we have. Now, similar to this, which we are talking about, now if I talk about an object which has got a spin 3 by 2, then you will say that if it has got a spin 3 by 2, then there are 4 possible projections, plus 3 by 2, plus half, and minus 3 by 2. Then if I talk about, no, I want that whatever my particle is, that should have a spin 3 by 2 and projection plus 3 by 2, then the answer would be a spin 3 by 2 whose projection is plus 3 by 2, then the answer is all the 3 objects are in the spin up state. This will represent for the spin a 3 by 2 plus 3 by 2 state. Therefore, this is 3 by 2 plus 3 by 2 state representing a spin. See the projection. Similarly, we can have 3 by 2 minus 3 by 2 spin, and then like here we have particle in state 1 is spin down state, in state 2 in a spin down state, in state 3 in a spin down state. Now if I ask you the question that if I put spin and isospin together and talk about a delta plus plus which is in spin plus 3 by 2 state. That means I know a priori the spin projection of delta plus plus, and I am telling you that it is plus 3 by 2. Mind it, if the particles are unpolarized and 1000 of protons, for example, I am talking about, and these 1000 protons are unpolarized, then 500 of them will be in a spin up state and 500 will be in the spin down state. It is only when you apply magnetic field, then you can talk about all 1000 of them will have a particular spin projection. Similarly, here in the case of delta particle, any delta you talk about among those 4, delta plus plus, delta 0 or delta minus, if I say that I have got 1000 delta plus plus, what will be its spin projection? They are not polarized. The answer to that is 250 of them will be in spin plus 3 by 2 projection state, 250 of them will be spin plus half projection state, 250 of them will be spin minus half projection state, and 250 of them will be spin minus 3 by 2 projection state. But to make life simple, what I am telling you, that I am giving you a delta plus plus and whose projection is plus 3 by 2. What will be its wave function when you will consider spin and isospin together? Then that means I am talking about all 3 objects as U and U in state 1, U in state 2 and U in state 3, and then plus 3 by 2 means all 3 of them are in a spin up state. And this is where I told you that your Pauli exclusion principle is in trouble, and that is why we introduced a quantum number that we called it as color quantum number, and this was red, blue and green. Okay. Therefore, similarly, if I ask you the question, I want a delta plus plus particle whose spin projection is minus 3 by 2. Then what will be the answer? The answer will be they will remain U, but their projections will be in the spin downward direction. Again, you are violating Pauli's exclusion principle. And that is why you will add red, blue, green to this U. If I say that I want to write the wave function for delta minus whose projection is minus 3 by 2, then this will be D, D and D. All three D's, and all three of them are spin downward, in the spin downward direction. Okay, therefore here when we are developing a general formalism, we have to keep in mind that their spins and flavor wave function can be simultaneously understood. Now the question is, what will happen when 1 plus 1 will combine with half minus half and 1 0 will combine with half plus half? Therefore 1 plus 1, that is combining with half minus half, and 1 0 is combining with half plus half. Now this we saw that plus 1 minus half will give me plus half, but plus half projection we can get it from 3 by 2 as well as we can get it from half. That is why yesterday we wrote it as half, 1 half 3 half plus 1 minus half plus half, 3 by 2 plus half, and then plus 1 half half plus 1 minus half plus half, half plus half. And this I told you that let us write the Clebsch coordinate, which is a real number by C1, and this is representing a delta plus state, plus C2, this is representing a proton state. And then for here, when I am combining this with this, 1 0 with half plus half, then we have 1 half 3 by 2, 0 plus half, 3 by 2 plus half, plus 1 half, 0 plus half, half plus half. This is C2 psi delta plus C3 psi delta plus C4 psi proton. And on the left hand side, what we have, 1 plus 1 is 2 U quarks in state 1 and state 2, and then you are adding a D quark, and 1 0 is 1 by root 2 UD plus DU, and then you are adding a third object, and that third object is a U quark. Therefore, what equation you have, UUD, those are known, C1 is known, delta plus C2 psi proton, and here you have 1 by root 2 UD, I am bringing this U inside, plus DUU, this is equal to C3 delta plus C4 psi proton. Therefore, what is unknown is this psi delta plus and psi proton. All of the other things are known, and we have got two equations and two unknowns. Just we have, this is 8th class algebra. From here we will evaluate, yesterday we have seen the value of C1, C2, C3 and C4. We will evaluate the values for psi proton and psi delta plus. This is what we have done. Then we are left with the possibilities that what will happen when 1 0 will combine with half minus half, and 1 minus 1 will combine with half plus half. Then this will give us 1 half 3 by 2, 0 minus half, 3 by 2 minus half, plus 1 half, 0 minus half, half minus half. Let us call them by C5, 3 by 2 minus half, plus C6, half minus half. And here this will be 1 minus 1, half plus half. This is 3 by 2 minus half. this is 3 by 2 minus half, then 1 half half minus 1 plus half minus half, this is half minus half state, this is C7 3 by 2 minus half plus C8 half minus half. Now the Klebsch-Gordon for 1 half 3 by 2 0 minus half, this value is root 2 by 3. This C5 is root 2 by 3, and when we have 1 half 0 minus half, this value is 1 by root 3. As I have told you, these are all real constants, and then this C7 is 1 by root 3 and this C8 is minus root 2 by 3. Therefore, like yesterday we wrote about C1, C2, C3, C4, here we are writing it as C5, C6, C7 and C8. And what we know, that the left hand side is known. This is 1, 0, that means 1 by root 2 ud plus du, and then you are combining a d quark. And this is 1 minus 1 is, there are two d objects, and then you are combining a half plus half object. Therefore, again you are getting two equations and there are two unknowns. What are those two unknowns? This 3 by 2 minus half, that represents a delta 0, and half minus half, that represents a neutron. Again you have got two equations and two unknowns, and those are the flavor wave function for delta 0 and flavor wave function for the neutron. Therefore, this is what we have discussed. Now this is described in these notes for C1, C2, C3, C4 as we have discussed this yesterday. Then for delta 0 and neutron, we are writing this. Again notice this delta plus wave function, this is again completely symmetric. You interchange the position of these objects u1, u2, d3 plus u1, d2, u3 plus d1, u2, u3. For the delta 0 also completely symmetric. While for proton, first two are symmetric, the third makes it anti-symmetric. Therefore, we are calling it as mixed symmetric, and similarly this is also mixed symmetric. Therefore, when we are considering these objects, we are finding out that proton and neutron wave functions, they are coming as mixed symmetric wave functions, while all the deltas, they are basically symmetric. Therefore, delta plus, if you recall, that was all u's, delta minus was all d's, delta plus is this, again symmetric, delta 0 is symmetric, while proton and neutron, they are mixed symmetric. But up till now what we have done, we have not still combined 0, 0 with half plus half object or 0, 0 with half minus half object. This we know that 0 plus half will give us plus half and 0 half will give us only half. Therefore, with half we cannot describe delta. Here we have only proton. Therefore, the important point is that when you will start considering 0, 0 with half plus half, what you will realize that what you have 0, 0, half plus half, you are getting only the proton part, and this Klebsch-Gordon is 1, this is C, and this was 1 by root 2 ud minus du, and half plus half is u. Therefore, for this you are getting also a result for the proton. This is 1 by root 2 ud minus du times u, and this you can bring it inside. This will be u du minus duu. Now when you will combine, instead of plus half, when you will combine minus half, then this will be minus half, minus half, minus half, and that will be, see, again this Klebsch Gordon is 1 and half minus half represents a neutron. Since you are talking about half minus half, therefore instead of U, you have a D. This is what we have listed. First, for when we consider 1 plus 1, 1 0, 1 minus 1, and with half plus half and half minus half, then I took the case when 0 0 is combining with half plus half, and this is what we are getting. As you can see, this is also mixed anti-symmetric wave function, and then this is half minus half. For the neutron, we are getting again the case. Therefore, this is for the proton, this is for, there's no need to write for proton or neutron. Just for to make life simple, I have written proton or neutron, because we are talking about 3 non-strange quarks. Those are U and D, and these 3 non-strange quarks are making a baryon, and that can be only for isotopic spin half whose projection is plus half, and isotopic half whose projection is minus half. Now once we are ready, we are through with this flavor wave function for the proton, neutron and all the 4 deltas. Besides that, there is an important catch, that if we talk about the spin wave function, you see that life is not going to be different. Just you have to replace it by an spin du. Instead of U, you talk about a spin up state. Instead of D, you talk about a spin down state. That is why I have tabulated it here, that if you talk about spins, combining spins of the particles, you have to replace it by a spin U with a spin up state and D with a spin down state, and that means here it will be 1 by root 2 up down minus down up, and then U3, that means this guy is up 3, and this will be the spin wave function. Let me just write it in the bracket, of a baryon whose spin is half and whose projection is plus half. Similarly, for the other case, you see this is also anti-symmetric. For the other case that we talked about, this guy, the equivalent spin wave function will be 1 by root 2 up down minus down up, and then we are adding the third state a down quark. Therefore, up down down minus down up down. This is what we will get for the flavor wave function and for the spin wave function. Now, an important point comes, that we had started with this concept yesterday, that actually to get an observable, we have to use the wave function, and the wave function was arising from the different combination. First, the localization in space, is isotopic spin, is spin of the particle, and the color. Now, if for example, if I want to evaluate the charge of delta plus plus using the quark model, then this will be the expectation value of the charge operator between these baryonic states, and that will be CR psi I psi S psi color, the charge operator psi R psi I psi S psi color. Now notice there is one important point, that we are talking about the charge operator. Charge operator will always operate on flavor wave function. It cannot operate on spin, it cannot operate on color or space. Therefore, that means what I meant to say is the following, that when the charge operator operates on the u quark, then this will give us 2 by 3 the electronic charge, and it will return back me the state. When the charge operator will operate on d quark, this will give us minus 1 by 3 the charge of the particle, and it will return me the state. Therefore, the important point is that this charge operator has nothing to do with this guy or this guy or this fellow. Therefore, we will write it as psi r, psi r, psi s, psi s, psi color, and then for the psi isotopic spin, the charge operator psi isotopic spin. And you see, these are all normalized wave function. These values will be 1. Baryons are color singlet. Then that means ultimately what you are required to evaluate, instead of this, just I can say that we are required to evaluate the expectation value for delta plus plus, and for this we are sandwiching the charge operator between the flavor wave functions of the delta plus plus. And therefore, if you are doing that, then we can write it as you recall for delta plus plus u1, u2, u3. Now you see there are 3 states where these quarks are living. Therefore, we write it as the charge operator 1, which will operate on the state 1, charge operator 2, which will operate on state 2, charge operator 3, which will operate on state 3. Then we have u1, u2, u3. Therefore, now you see, again, these are orthogonal state and these are normalized. Therefore, without proper normalization, never we can get an observable. Therefore, we can write it as u1, u2, u3, e1, u1, u2, u3. Then similarly we can write e2, and similarly we can write e3. Now e1 will operate on the quark wave function which is in state 1. E2 will operate on the quark wave function which is in state 2. E3 will operate on the quark wave function which is in state 3. Therefore, you notice when E1 will operate on the quark wave function, it will give me 2 by 3 times the electronic charge. These are numbers, we can take them out. Therefore, 2 by 3 and the electronic charge, that should also I write. And then this is U1, U2, U3, and then what we will be left with is U1, U2, U3. And then similarly for the second one, if you notice, this is for the first one. For the second one again, 2 by 3. Now this is going to operate on particle in state 2, but that will also give me 2 by 3 times this value plus 2 by 3 times that value. And this means that these are all normalized. This will be 1, and therefore the value that you are going to get from here will be 2 by 3e, 2 by 3e, 2 by 3e. And that will be how much? What I am talking about? 2 by 3e, 2 by 3e, and 2 by 3e. And that is nothing but 2 times the electronic charge. That will be for delta plus plus. Now, instead of evaluating individually particle in state 1, particle in state 2 and particle in state 3. You can verify that equivalently if I multiply here by a factor of 3 and only evaluate the particle which is in state 3 or for that matter in state 1, then you will get the same result. That means just I am taking the particle which was in state 3. That means I am talking about E3, U in state 1, U in state 2, U in state 3, and that will give me 2 by 3. Therefore, this will be 3, let us erase it, 3 into E3 operating on U3 will give me 2 by 3E, and that will be 2. Therefore, instead of doing it individually for the quark in state 1, quark in state 2 and quark in state 3, just we can take 3 times E3 and we operate E3 only on the particle which is in state 3. We will get a result that will be the same as when we take individual contribution from E1 operating on 1, E2 operating on 2 and E3 operating on 3. Try to understand what I am telling you. I am telling you that when we want to write flavor wave function for delta plus plus, what we have to keep in mind that isotopic spin should be 3 by 2 and the projection of the isospin should also be 3 by 2, and this way we are getting from here U in state 1 and U in state 2, and here for half plus half we are getting U in state 3. Similarly, when we add 1 minus 1 with half minus half, then we get D in state 1, D in state 2 and D in state 3. And you can see that like U1, U2, U3 which were symmetric, here also it is symmetric. You interchange the positions of these quarks, nothing is going to happen. Now what we do, we try to combine 1 plus 1 with half minus half, and then we will combine 1, 0 with half plus half. What we will see that when we will combine plus 1 with minus half, algebraic sum, this will give me plus half. This plus half projection I am telling you can come from 3 by 2 as well as it can come from half. Therefore, we are getting 2 terms, one with for the delta plus and another for the proton, and this C1 and C2 are the Clebsch-Gordan coefficient. Similarly, with 1, 0 half plus half, we will get 2 terms, one with 3 by 2 and plus half and another with half plus half. And this, say this is C3, this is C4, and the value for C1, C2, C3, C4 are tabulated here, where we know that this guy is 1 by root 2 UD plus DU, and then half plus half means U. Therefore, on the left hand side is known here, and on the right hand side we know C3 and C4. Therefore, the unknown quantities are here. The flavor wave function for the delta plus. Therefore, this is delta plus, this is proton, this is delta plus, and this is proton. You have got 2 equations and these are the 2 unknowns. You solve it, 8th class mathematics, and what you find out that this psi delta plus wave function is completely again symmetric. It contains 2u and 1d, and proton wave function is mixed symmetric because there is a negative sign over here. Therefore, the proton wave function is mixed symmetric while delta plus wave function is mixed symmetric. Similarly, delta plus wave function is completely symmetric. Therefore, similarly, if we want to combine 1, 0 with half minus half and 1 minus 1 with half plus half, then what we are going to get here? We are going to get here 1, 0, half minus half, 3 by 2 minus half. We are getting a 3 by 2 minus 1 by 2 state, plus 1, half, half, 0, minus half, half minus 1 by 2 state. This is again Clebsch-Gordan, say C5, this is C6, and then for 1 minus 1 half plus half, this guy, we are getting 1 minus 1, half plus half, 3 by 2 minus half, 3 by 2 minus half, plus 1 half half, minus 1 plus half, minus half, half minus half. Again, these are the Clebsch-Gordon coefficients. These are the two equations, and then you have two unknowns. 3 by 2 minus half means I am talking about delta 0, and half minus half means I am talking about neutron. Therefore, here also we see that we have the delta 0 wave function, which is completely symmetric, which contains two d quarks and one u quark, and neutron wave function is mixed symmetric. Now, up to this point, we have combined one isotope with half plus half or half minus half. Now we are left with this 0 0 guy, which we have to combine with half plus half, or 0 0 guy with which we have to combine with half minus half. Now you see, with 0 plus half, algebraic sum will give you plus half, and 0 half can give you only j equal to half or I is equal to half, and half cannot have a projection. Minus 0 and half can give you only half, and half will have a projection plus 1 by 2 or minus 1 by 2. When I am considering this, therefore the term will be 0 0, half plus half, half plus half. I am getting a half plus half state. This will correspond to a proton, and similarly when I will consider minus term, this will correspond to a neutron. And notice that 0 0 was our anti-symmetric state. Therefore, here what we are going to get is two anti-symmetric state, one for proton and another for neutron, while here these four are the symmetric state, completely symmetric states for the deltas, mixed symmetric states for the proton and neutron, and then mixed anti-symmetric state for the proton and neutron. Therefore, for proton and neutron, we are getting a combination of mixed symmetric and mixed anti-symmetric state, while for delta, we are getting completely symmetric state. Now, when we talk about the spin of the particle, then just we are required to replace u by the up quark, up spin, and d by the down spin, because if I talk about deltas are spin 3 half particles. It can have 4 possible projections again for spin, and for nucleons, whether I am talking about proton or neutron, that is also a spin half particle that will have a projection of plus half or minus half. The important point is, if I am considering plus half spin projection for proton, then there is no reason to consider the minus half spin projection for the neutron. Therefore, initially I am writing it to have the same analogy what we did for flavor, spin wave function half plus half proton, but the same is true for the neutron. The same is true for the here proton, because if I am choosing, for example, if I want to take the ratio of magnetic moment of the neutron upon the magnetic moment of the proton, then the charge operator and the flavor wave function that we will talk about, flavor wave function will be different, but spin wave function for both proton and neutron will be the same. It depends upon our choice whether we want to have plus half or we want to have minus half. Similarly here, this can be equally good for neutron, mixed anti-symmetric, or equally good for proton. Therefore, what we can do, we can take this half plus half and half. When we will do the magnetic moment, we will take this term, these two terms, but equally good choice would be one can take these two for proton or neutron spin projection to be minus half. Now, to have the baryonic wave function, we have the space part, isotopic spin part, and the color part. For delta, since delta has to be, this is baryon, the wave function should be anti-symmetric. Therefore, AS I have written for anti-symmetry. Then space part is symmetric, isotopic spin part is symmetric, and the spin part is symmetric, only the color part is antisymmetric, and this color antisymmetry term is making the complete term to be antisymmetric. And when we are evaluating the charge of the delta plus plus, then we are reaching charge operator between this flavor wave function, which is antisymmetric. We are writing all the four components, and since we know that the flavor wave function contains u, d, etc., and the charge operator will operate on say u state to give us, this is say the charge operator. This will give me 2 by 3 the electronic charge, and it will return back the u state. D will give me minus 1 by 3 electronic charge. Therefore, all these are properly normalized wave function, which will simply give us 1. Only we have this term. But when we will talk about the proton, then there is a catch, because proton wave function, here if you notice, this part will be symmetric, but these two contains mixed symmetric and mixed antisymmetric term. Overall the term should be symmetric because this guy is antisymmetric. Therefore, there what we are going to do, mix symmetric for isotopic spin, mix symmetric for spin, plus mix antisymmetric for isotopic spin, and mix antisymmetry for spin divided by root 2. Therefore, when we will talk about proton, for this part we will write in this fashion, and then these two will be there. Therefore, this part, as you can see, this will be symmetric. This mix anti will give me symmetric. Therefore, we will get a symmetric part from here, and symmetric part is for space, and color is antisymmetric. Therefore, when we talk about proton or neutron, we have this term instead of these two separately, because these two were symmetric by construction which we have obtained. And therefore, the point is that when we write psi p, we write in this way, and then we again say that this charge operator is going to operate only on the flavor state. Therefore, finally we have these two terms. And that means if we are talking about proton, then this is a half minus 1 by root 6 u du plus d uu minus 2 uud. The charge operator, the same guy here, plus 1 by root 2 udu minus duu, the charge operator, and then 1 by root 2, the same thing. This is what we have to evaluate to get the charge of the proton. Similarly, if we want to get the charge of the neutron, then we have to write this, we have to evaluate this, and psi n will, again this part will remain the same, this part will remain the same, this part will remain the same, and up to this point. What is going to change? Here the flavor wave function which we have written over here, as you can see, for the neutron, this will change to evaluate the quantities. Okay, let us stop here, and in the next class we are going to discuss how to evaluate the charge of proton and charge of neutron, and the magnetic moment of the proton and magnetic moment of the neutron. Thank you very much.